Okay, good afternoon, everyone. Let's get started. So, today we're going to talk about the last topic, about purpose learning. It's actually one of my favorite topics, calculus processes. Unfortunately, due to the time limit, we can only give some like fundamental introduction on that. But if you're interested in some sort of study of Gaussian processes, there's a well-known book. It's called Gaussian Processes, Gaussian Process for Machine Learning. It's a very good reference book and talk about every aspect of Gaussian process. Yeah, I would like to mention that Gaussian process. It's kind of amazing model in that, like nowadays, people talk about artificial intelligence, people talk about machine learning. They usually refer to are referred to as neural networks. But in many cases, like at least from my own experience, the benefit of using neural network is less than using Gaussian process. Especially you don't have that much data, like you might better first try Gaussian process. And it's little efforts because it's not like neural network. You have to prepare GPU hardware, right? You have to tune like architectures, all kinds of hyperparameters. Just run Gaussian process, use one simple kernel like RBF kernel or square exponential kernel. It can tell you if it works or not. Okay, so here's the plan for our discussion. So first, I'm going to introduce the Gaussian process regression network. Gaussian process regression model. And we'll talk about how do we train a Gaussian process model, how do we make prediction. And then we'll review some profound connection between the Gaussian process and Bayesian neural network. It turns out that when your neural network width goes to infinity, meaning that you have an infinite wide Bayesian neural network, then the output of neural network is essentially a Gaussian process. So that's an amazing thing in a Gaussian process. Okay, so first Gaussian process regression, right? So so far we have talked about many priors, right? So we know that the Bayesian modeling technique or the art is essentially how do you construct different types of priors, then combine with data so that you can integrate your prior knowledge and the data information to get the posterior. Okay? So, but all the priors we have discussed so far are over numbers, vectors, or matrices, right? We're talking about the priors over those quantities. And what if I want to create a prior for functions? Because I want to learn function, right? And learning function learning is kind of like a critical or central topic in machine learning, right? From the data, you want to learn mapping from the input to the output, right? You can use neural network, you can use linear regression or generalized linear regression. They all kind of assume some kind of parametric form of your function, right? You're just to identify the parameters of those function, parameterize the function form, right? And so that you assign a prior over those parameters and over those quantities. And now let us do not assume any parametric form of your target function. Let's just create a prior over functions. How can we do that? So suppose our target function is defined as a mapping from a d-dimensional input space to a real space, right? And we want to place a prior over this function, and then given the measurement of this function at a set of locations, at different inputs, values, right? You want to infer the posterior distribution of your target function. So that's our goal. So Gaussian process perhaps is the simplest yet most widely used way to construct function priors. So yeah, we know how to place prior over like several random variables. Say for a random variable vector z, it might contain m values, right? So we can assign prior over all those m values, like for example, multivariate Gaussian distribution, Dirichlet distribution, whatever you want, right? And then let us consider constructing prior over functions. So what's the difference between functions and a finite number of random variables? Any thought? We know function is actual mapping, right? Given any instance in input domain, you're going to map it to a value in the output domain, right? That's our definition of function, right? So let us use a seemingly naive view of function definition, right? So previously we thought okay, function is a magic mapping from some input space to output space, right? And now, if we list all possible inputs in the input space and their corresponding function output in output space, we can view them as a big table. Like for example, if I just enumerate all possible input in possible space, input space like x1, x2, x3, and so on, the output will be a super long vector, right? F of x1, f of x2, f of x3. Well, you can enumerate every possible input, right? And you have the collection of all possible function outputs. So conceptually, you can view a function as a big table or infinitely long vector. Does that make sense? So this is the essence of function, right? Function is nothing different except that you can view it as a super long or infinite dimensional vector. That's it, right? So previously, what we have done is that we're gonna assign a prior over a finite dimensional random vector, right? And now, if we deal with function, that means we're gonna assign a prior over an infinite dimensional long vector. Those long vector includes all possible function outputs. So then the next question is, oh, by the way, I have to mention that rigorously speaking, we shouldn't use a table to, we shouldn't say we can use a table to organize all the function outputs, because the output of function is usually infinite and uncomfortable, right? Because all the inputs, say from some real space, you cannot index every input through some integers, right? So if you know the some representation theorem in the real L space, it's not it cannot be, it is called uncountable, right? But basically the concept is that okay, we can view the collection of all possible function outputs as a super long, infinite many uncountable vector, right? And our goal is to create a probability distribution over this vector as our prior for the function. Does it make sense? Any question? Okay, so that's the key idea, right? So Is it doable? The answer is yes. And also there's a rich solid theory supports construction of such a prior. This kind of prior is called random process. Okay. So when we assign a prior over a function, and then this distribution over this function is called a random process. You might have heard of random process before, right? Now let us look at a more formal definition of random process, right? And see how it is associated with the prior of the function, right? So we view random process as a function of two variables. One is t, one is omega. So here we're assuming, okay, our input domain can be viewed some kind of continuous time, but it doesn't matter because this t can be replaced by any input in your own in your domain of interest. Right? Right. The time t here can be generalized to any continuous input. Right? And omega here is the random sample. Right? If you can recall, at very beginning of our semester, we introduced the definition of random variable. Right? So random variable is not a variable. It's not random. Random variable is a mapping. Random variable is a mapping from the sample space, okay, to some real space. Right? I mean, narrowly speaking, of course, you can map it to any other space. Right? So random variable typically like take some random experiment outcome as the input, right? And you map it to a real value, right? That's called a random variable. Right? And random variable, the real value itself doesn't have any randomness, right? The randomness comes from the experimental outcome, right? Like you toss a coin, whether you see it heads up or tails up, you roll a die, right? Where the points you have seen, like 1, 2, 3, 4, 5, 6, right? So your probability space is defined on this sample space and even space, which is usually a sigma algebra, and a probability measurement, right? If you can remember, right? This even space is called sigma algebra, define all collection of the events, random events you're interested in. For example, you might be interested in if your point, right? When you roll a die, the point is less than 3, bigger than 5, and so on. Right? And then this probability measurement maps every event to a number between 0 and 1. It tells you what is the probability of each possible event. Right? And the random variable is to map every possible random outcome in your experiment to a real number so that you can handle and analyze everything in the real space and can do very rigorous analysis. That's the motivation of people like why invent random variables. So now, if we extend our definition of random variable, right, we define a function or mapping, not only a function of the sample space in our original probability space, but also a function of some t, like some index t. Like this t can be time or can be any input variable you're interested in, right? Right. Then we call this function as a random process. Right? So if we fix t, meaning that we fix the time variable or any input variable, then we know that xt omega is just mapping from omega to some r, right, to some real value. Then xt omega will be a random variable, right? Maybe I can use one example to make it more concrete. For example, t is the time. T really is the time, and And xt omega just represent how the temperature varies along with the time. Okay? And omega represents whatever random weather conditions, right? And you're gonna map these weather conditions to some value like temperature, like precipitation or pressure, all those kind of stuff. So you can see that if you fix T, say right now, then your temperature or pressure, whatever, is a random variable. Like it maps some random weather outcome to some measurement value. On the other hand, right, if you fix omega, meaning that you fix the random experiment outcome, right? And then you just look at the curve, how the output of X vary along with T. Then we know that this is a function of T, right? This is a function of the input index T. Right? Then, you kind of map a random outcome to a function curve. Okay? Take like family as example, right? If you look at your random outcome, it might be just 1, 2, 3, 4, 5, 6, right? And the point 1 to fix the omega to be 1, right? And your function, you have one function curve, right? You fix omega to be 2, you have another function curve. You fix your point to be 3, right? You have a third function curve, right? So you can see there's a mapping between your outcome of a random experiment and some function, rather than just a value in the real space. So this is the two wheels of the random process. Right. So if you take a look at this figure, right? So this represents a random process, right? So the x-axis is the input t, and y-axis represents the random sample omega, right? So you can see that if you fix the random sample, right, in the sample space, if you just observe the random process, it will become some function, right? And on the other hand, like if you fix the time point like t, say t1, right, and if you look at the outcome x, right, because different omega will lead to different outcome of x, t, and omega, right? So this is a random variable because when you have different omega here, you have different randomness, and then correspondingly, you have a different probability, density, or mass over the outcome of the random variable. Does it make sense? Any question? Yeah, everyone is comfortable, right? Okay, so now let us consider if we want to sample some function, right? So from our previous discussion, we have seen like, okay, for random variable, right, general, for ordinary random variable, what you need to do is just map every possible random outcome in your experiment to some real value, right? Say your outcome 1 give real value 0.5, outcome 2 give real value 0.6, right? So now for the random process, I'm no longer map this outcome to particular values in the real space. Instead, I'm gonna map each outcome to a function curve, right? So for omega 1, your mapped function curve could be like this, right? For omega 2, your mapped function curve could be like this, right? And for omega 3, your mapped function curve could be like this, right? So this is around the process. So it looks like the framework is very appropriate to create the prior over functions. Then what kind of process should we use? And here we use a Gaussian process. So what is Gaussian process? So Gaussian process is a particular type of random process such that for every finite collection of those random variables, meaning that you pick up any finite set of t or x, here should be x, right? And those random variables will follow a multivariate Gaussian distribution. Okay. So this is the definition of Gaussian process. Any question? I mean, if you look at random process, it's a very giant definition. It's a big range where you can create whatever mapping from the sample space to the function space. Okay? But now, if you're doing Gaussian process, okay, I'm gonna add some constraint. I will require that for my mapped curves, right? We know that for any fixed input x, the corresponding mapped function value should be a random variable, right? I require that for any collection of the fixed inputs, the corresponding function value must be jointly following the multivariate Gaussian distribution. So this is called Gaussian process. And someone asked, okay, can I create other random process as a part? The answer is definitely yes. You can define whatever random process you like to serve as a prior for the f for the target function f. Like for example, you can require that, okay, for any collection of inputs, those mapped function curve values, they must jointly follow student t distribution. This is called student t process. And actually, student t process tends to be more robust than the Gaussian process. Although the Gaussian process is way more popular simply because it's easy and convenient to use. So now let us look at this definition of Gaussian process. What does it tell us? Right? So given any finite set of inputs, like x1 to xm, we can look at the corresponding function values, right? As we mentioned, for any input, the function value sampled from the Gaussian process, it must be a random variable, right? And from the definition of Gaussian process, these n function values, namely n random variables, must follow a joint Gaussian distribution, right? So what's the form of this joint Gaussian distribution? So first, the mean of this joint Gaussian distribution is usually set to 0. But you can also assign some mean function, which can also vary with x. Here, we just choose the most common setting, like we assume that the mean is simply 0. And then we got a covariance matrix that way. So the covariance matrix is usually constructed from some kernel function. So what is kernel function? Kernel function is a function between two input, function of two input that give you some value, right? So the covariance matrix is computed by evaluating all possible pairs of inputs in this set. So suppose you got n inputs, right? So you got n square pairs, right? That form this n by n covariance matrix. So every entry of this covariance matrix is computed by the kernel function over one pair of the inputs. That's the form of the finite distribution of the Gaussian process. So what does kernel function mean? Right? Kernel function measures the similarity of two inputs. Here is one of most commonly used, perhaps the most popular kernel function, which is called RBF kernel or square exponential kernel. You have taken my machine learning class before. You should have seen this, right? So it just calculate Euclidean distance between the two inputs and divided by some length cube parameter tau. Take negative, take exponential. That's it. So you can see that the closer the two input vectors, the larger the kernel function value, right? So at it is the largest can be 1, right? Because when xi equals to xg, this guy to be 0, so exponential to the power of 0 is simply 1, right? But if xi and xg are very different, say this Euclidean distance is large, then you take exponential exp to the power of negative of that distance can be close to 0. Okay. So if we look at the covariance matrix, right? So the covariance matrix is actually tells us what is the covariance between the function value at the corresponding inputs, right? For any entry of the covariance matrix. This covariance between fxi and fxj at the entry ij, right? So now we calculate covariance matrix with this kernel function of their corresponding inputs. What does it mean? It means that I'm gonna use the similarity of the inputs to describe or determine the correlation about corresponding function outputs. It actually makes sense. Why? Because function, in the practical world, the functions we're interested in is often continuous. Continuous means that, okay, the closer the input, the closer the function values, right? That's the definition for continuity, right? And we know that, okay, if x1 goes to x2, then the function output will go to the function output at x2, right? And of course, we're using probabilistic view of that. We wouldn't say, okay, fx1 will be equal to fx2, right? We're going to use some statistic term to describe that kind of relationship. So we use covariance function, right? So it tells us in our Gaussian process modeling, the closer or the more similar the inputs, right? The more correlated of the corresponding function outputs. So that's the key idea. Remember, in the probabilistic model, we view all those function values are random variables. We couldn't say random variable A must equal to random variable B, right? So here we use correlations to represent their relationship, right? And our underlying assumption is that the strength of the correlation between two random variables is determined by the similarity of their inputs. And the larger the similarity, the stronger they are correlated. And also, the similarity is measured by your choice of kernel. Does it make sense? Okay, so through the definition of the kernel function, it essentially implies that the closer the inputs, the more correlated the function outputs. Okay? So it describes the function smoothness in the probabilistic context. Any question? Yeah, I hope everyone is happy about this because when I was studying, when I started to learn Gaussian process, I was kind of confused for quite a long time about this. I was confused why people saying, okay, Gaussian process is so flexible, you never assume any parametric form of the function. The reason comes from here. So the modeling of Gaussian process actually through the correlation between or the covariance between the function outputs. It's just through this Gaussian distribution. Okay? And this Gaussian distribution, we know the mean is 0, right? We mainly care about the covariance between different function outputs. And then we just characterize the covariance between function outputs while the similarity of their inputs.
So you can see that you don't need to assume any parametric form of them. You just need to assume how much strength of their correlations of the functions output correlations. That's why it appears to be very flexible. David. Yeah. You mean from this, how do you predict the value of the functions and let them look like continuous? Okay, that's a very good point. Let's talk about let us discuss about it when we talk about the prediction. Okay. But anyway, so far, is everyone feeling comfortable? This is how the philosophy of Gaussian process. It doesn't assume, okay, your function is a linear function or a polynomial regression function or a neural network. It doesn't make such an assumption. It just assumes, okay, your function outputs should be correlated in a way your kernel function defines. And that's it. That's why AX-based flexibility, right? It's not restricted to any form of the function and parametric form of function. So there are numerous ways to define a kernel function. That means there are numerous ways to characterize the similarity of the inputs. That actually tells you what kind of functions they can learn from data. Right? So now, with this Gaussian process prior, let us talk about the Gaussian process regression. And given the training data, how do we predict the values at the function values at new inputs, right? In practice, we'll never need to sample the whole function, although in theory, we indeed assume the function is sampled as a Gaussian process, right? Because in the practice, the training data are always finite. Suppose we only connect, we can only connect like n training examples, right? Then we can focus our prior only on the function values on this n training inputs. That will be a multivariate Gaussian distribution. So given the training inputs X and training outputs Y, and so first sample the function values at those inputs. We denote them by F, right? Those bolded F, meaning the n function values n, right? So because the whole function is assumed to sample from a Gaussian process, then the finite value in this function curve, namely fx1 to fxn, will follow a multivariate Gaussian prior distribution and has this form, right? This is what we just discussed. And then given f, we sample the observed outputs. Right? And the outputs could be noisy, right? So if the outputs are continuous, we usually use a Gaussian likelihood to model the condition distribution of the output, actual output given your sample function values f. Okay. And here sigma square reflects the noise that can corrupt the actual the real function value to get the actual noisy observation. And then we can write down the joint probability about our Gaussian process regression model, right? So it is simply a Bayesian model, right? We have a f sample from a multivariate Gaussian distribution, and given f, we sample the noisy observation y. Okay, so this is a prior of f. This is a this is a prior of f, and this is a Gaussian likelihood of the noise observation. Okay? And we want to estimate two types of parameters. One is the parameters inside the kernel function. For example, in the RBF kernel we just discussed, there's one kernel parameter is called length skew. Right? So length skew also determines the similarity. And the other is the noise variance. So how do we estimate these two parameters, two types of parameters? We can marginalize out latent function values. This is a Gaussian, and this is a Gaussian. When you marginalize out, it will become another Gaussian. Why? Because from this likelihood, we can view Y as F plus some independent noise, right? And this independent noise sampled from zero mean Gaussian with covariance sigma square I, right? And then that means your marginal distribution of Y will be 0, and the covariance of Y will be covariance of F plus the covariance of this noise, which is the kernel matrix plus the sigma square times identity. So you got this marginal distribution of your noise observation given the data, given the training inputs, and given the parameters data. Then in the next step, right, you can just maximize the log marginal log marginal probability to estimate data. And that's it. That's how we conduct Gaussian process regression practice. Any question so far about this training procedure? Everyone is comfortable? Okay. So I would like to talk a bit more about kernel. Right? So we said that we use covariance matrix. We use kernel function to calculate our covariance matrix. Like every pair in the covariance matrix, every entry in the covariance matrix is a kernel function over a pair of the inputs. Right? But remember, the covariance matrix must be a positive semi-definite. So that means the kernel function, if it is valid, it must satisfy some conditions. Right? So this is called a Moser's condition. Right? So a valid kernel function must ensure that for any finite set of the inputs, we use kernel to compute the kernel matrix of that. That kernel matrix must be always a positive semi-definite. Only in that case, you can say, okay, you can say, well, you use your kernel matrix as the covariance matrix, it is valid. And otherwise, it is not valid Gaussian distribution. And how do we construct kernels, right? There have already been many popular and classical kernels, like linear kernel, polynomial kernel up to degree D, RBF kernel, as we just mentioned, periodic kernel, Merton kernel, and so on. So it's very rich. And in addition, you can also construct new kernels based upon old kernels, like you can add two kernels together, they will form a new valid kernel. You can multiply two kernels together, they form a valid kernel. Right? So there's a nice property of the kernel function, means that for any valid kernel function, there exists a high dimensional nonlinear feature mapping such that the kernel function is equal to the dot product after performing the feature mapping. Right? And usually, this feature mapping, associated with some kernel, is infinite dimensional. So that means that from practical perspective, you won't be able to really directly compute this feature mapping and do the dot product. In other words, kernel function is a cheap way to compute the inner product about high dimensional feature vectors. Right? That's one advantage of the kernel function. But this is not the major point we want to discuss today, because we have discussed about it in the machine learning class. We talk about SVM, we talk about kernel trick, right? It is important to generalize a linear regression model to nonlinear regression model through some feature mapping trick, right? Here we just want to refresh our mind about the property of kernels. So now, through this property of kernel, right, we can have another view of the Gaussian process regression, which we call linear model view. So as we mentioned, right, if you choose a kernel function, x1, x2, we know that it means you're equivalently, implicitly compute the dot product there over the feature mapping on two input vectors, right? Okay. So now let us assume that, okay, I'm able to compute such a feature mapping, although practically it's infeasible. We'll just do some theoretical analysis, right? Now I'm gonna first sample an infinite dimensional Vitti vector W, right, from a standard Gaussian part. I'm talking about, and now I'm now creating another probabilistic model, right? In my model, I'm gonna first sample W from standard Gaussian distribution, and then I sample the observed output by this Gaussian likelihood, a Gaussian distribution where the mean is the inner product between W and the mapped feature vector, and the variance is sigma squared. Now my claim is that this model is equivalent to the Gaussian process regression. Why is this true? Because when we marginalize our W, right, for our model, right, you will see that the marginal distribution of all your training outputs, given the training inputs X and theta, has the exact same form of the Gaussian process. Why? How can we see this point? Yeah, let us do a little bit manual things, right? So from this model, we know that, okay, each example Yn can be written as W transpose psi n. So here, for simplicity, I just write psi n as psi xn, okay? And plus some random variable to say epsilon and epsilon n sampled from a Gaussian distribution, zero mean, and zero mean and variance is sigma square, right? So now if you write down all the Yn in this way, if you look at the Y vector, meaning all the output vector, like observed output vector, you can view it as a big psi matrix times W plus a random noise vector, right? And here's a big psi matrix. You just put each psi n in a row, right? Does it make sense? Okay. I can write down my training output vector Y as this feature matrix psi W times W plus some noise vector, random noise vector epsilon, right? And this noise vector is sampled from a Gaussian distribution with covariance as sigma square identity. Does it make sense? So now we know that, okay, W is from a Gaussian, standard Gaussian, right? And this epsilon from another Gaussian distribution, they are independent. So Y essentially is a linear transformation of the Gaussian variables. So what's the distribution of Y? Any thought? Don't be shy. Yeah. Yeah, it's still Gaussian, right? Your linear combination of Gaussian variables is still Gaussian, right? And the mean of it is obviously simply 0, right? So what is covariance? There's some formula, I just write it down. So it's just a psi covariance W psi transpose plus covariance of this epsilon. Right? I mean, you can manually check this. I just recite the formula, right? So the covariance of W, just identity, right? So the covariance actually is psi transpose plus the covariance of epsilon is sigma square identity, right? And that means your Y will follow 0 mean and this covariance. So now let us look at what does this matrix mean, right? So this psi transpose equals to, remember this is definition of psi, right? Psi is actually every row you contains a mapped feature vector, right? So you got psi 1 transpose to psi n transpose, right? If we do psi transpose again, it becomes psi 1, psi 2 to psi n, right? Each column is your feature vector, right? Now, if you do the psi transpose, you will see n by n matrix, right? And every entry is just the dot product between a pair of these feature vectors, right? And so on. This is psi 2 transpose psi 1, blah blah blah, psi 2 transpose psi n, and so on. Right? This is what your psi transpose matrix looks like. So now, because each entry of this psi transpose essentially is psi I transpose psi j. Right? What does this mean? David. Yeah, it's actually the value of the kernel function. It's just actually the value of k, xi, and xj. Right? That means this psi transpose matrix essentially is the kernel matrix. So now we can see that, okay, you use this generalized linear model, which is equivalent to the Gaussian process model, right? And here we just need to apply a feature mapping which corresponds to the kernel function used in your GPU regression model. So now I have introduced the model. I will introduce how the GP prior is created and what's the property of the GP prior, namely any finite for any finite input, the function values must follow a multivariate Gaussian distribution, and then the covariance matrix is computed from the kernel, and it just means the Gaussian process will model the function values only according to their correlations, right? And then we give an interesting view of the Gaussian process from the linear model view, right? That means like if you are able to really construct the implicit feature mapping of the kernel, you can convert it into an equivalent linear model. So next, training and prediction, right? As we just mentioned, right? For the Gaussian process regression, because both the prior and likelihoods are Gaussian, and you can marginalize out the hidden variable f, right, to get the marginal likelihood about the actual output, and you maximize this marginal model probability or or is also called model evidence, to find out a kernel parameter and noise variance, right? This is called type 2 maximum likelihood estimation. So how to make a prediction? So suppose we got a new input x star. I want to know what is the function value of x star given the training data. So here we're going to leverage the definition of Gaussian process, right? Because whole function is assumed to be sample as Gaussian process. That means the test function value of x star and all the function values at all the training data, x1 to xn, they also follow a drawn Gaussian distribution or multivariate Gaussian distribution, right? So that means you can write down their distribution is zero mean, and then you're gonna have this giant matrix, right? And in the top is just k x star, and then this block and this block are just this one are just the kernel matrix, your training data, right? Right, and this one is the cross kernel from x star to all your training inputs. And similarly, this part is your cross covariance between the training inputs and your test input x star, right? Okay. So now, because we only observe the actual output y, right? We know that the actual output y is just the training input. No, the function value is at training input, so x1 to fxn plus some noise, right? So that means you can have your joint distribution between fx star, your function value at test location, and y also as a Gaussian distribution. The only difference is that, okay, for this block, you have to add a diagonal matrix sigma square identity, right, to account for the noise inside y. Then you have this joint distribution of the output at test location fx star and y. You got this block kernel matrix, right? So here is kx star x star, and here is the cross covariance between x star and x, the training input x. Here is its transpose, and here is the covariance of y, which is the kernel matrix plus this noise variance times identity. Any questions so far? Right. And then, if we want to compute the posterior probability of your function value fx star condition on y, we just use a conditional Gaussian, right? It's just apply the formula. Nothing else. So this is a predictive mean, and this is a predictive variance. And that's it. That's how we get the prediction of the new function value. And if we can look at the predictive mean and predictive variance, you see that. So first you need to compute the cross kernel between your test input x star and training input x, and then you compute the inverse of the covariance matrix for y, right? So it's kernel matrix plus noise variance times identity and times y, right? This essentially is a continuous function of x star, right? So the kernel function is your continuous function. So you can see that the predictive mean at all locations is kind of continuous to the input x, right? I think that answers your question, David. Like, although your model, okay, you only model the distribution for a finite number of the function values, but we'll make prediction because of this conditional mean, Gaussian conditional mean and conditional variance. Your prediction is still continuous with respect to the input. Right? And similarly, you can look at observation is still the variance, the conditional. You can also observe the predictive variance is also continuous function of X star. Okay, any question so far about the prediction about Gaussian process? Everyone's comfortable? Look like it's easier. Okay. So here we just want to show some prior samples of functions, and after training what is posterior function. So those curves are sampled from the Gaussian process prior without any observations, and those shaded regions just to show the prior variance. Right? You can view them basically as the diagonal of the kernel matrix, right? Because you're assuming, okay, for any set of points, your function mean is 0, and the variance, the covariance is the kernel matrix, right? If you take a look at any input, right, they should follow this multivariate Gaussian distribution. And if you look at their their individual variance, it should be the diagonal part of your covariance matrix, right? And usually, for the same input, the kernel function value won't change. That's why you see this shaded region, they don't vary. It's just a kind of like rectangular. And the sample of these functions is to how do we generate these curves, right? So the idea is that, okay, you're gonna pick a lot of samples in the input space, and then you sample the function value through a large multivariate Gaussian distribution, and then you connect the dots, you get those curves. And in theory, like if you make very, very dense sampling of the training inputs, and then sample the corresponding function values through this multivariate Gaussian distribution, you'll get your curve more accurate. Right? And then, say, if we observe 2 training points, right, and then we use this formula to compute the predicted distribution of your function value at the inputs in the whole input domain. So here's the result, right? So this dark curve is the dark solid curve is the predicted mean, and the shaded region is the predicted variance. At every point, like see here, you can pick up X value here. This might be 0.8 something, like that. You just apply this predicted mean and predicted variance. You can obtain the here and also here it's a standard deviation. You can compute the range of this region. So you can see that when you are close to the training inputs, your predicted variance reduced quickly, right? That means you are pretty confident about prediction. However, when you are getting far away from the training data, right? See here, then you can see your prediction variance, the predicted variance increases quickly. Why? Because they're far away from the training data. I'm not sure about my prediction. I'm not confident about prediction anymore. So this is very useful because Gaussian process can directly tell you what's your uncertainty about your prediction. Okay. Any questions so far? Okay. The remaining thing we want to talk about Gaussian process regression, we want to talk about its connection to Bayesian neural networks. So there is a famous conclusion drawn by Ralph Neal. He's a pioneer in deep learning and Bayesian neural networks. He pointed out that if your neural network has an infinite number of neurons, then your Bayesian neural network converges to a Gaussian process. How can we see this point? So let us consider a neural network with only one hidden layer. So here is the input vector x, and suppose in this hidden layer we have m neurons, and the weights on edges to generate each neuron, we represent them as by u1, u2 to um. And here, for simplicity, I did not like draw all the edges connecting every element in X to one particular neuron. That will be too tedious, right? So we can put all the weights together to represent as U1, U2 to UM. Then each neuron, say neuron J, its output can be computed by the dot product of the UJ with the input vector X and apply a nonlinear activation function. Okay. And then the output layer is a linear combination of the neurons from the second last layer. So the weights of the the linear combination are V1 to Vm. So this is how we get the output. Okay. Does it make sense? So this is our basic setting. Okay. Now let us look at the Bayesian neural network. Right? So to construct a Bayesian neural network for this architecture, we assign to each uj here the same prior, but with bounded variance. This is a very reasonable subform. It's really you don't want to assign some prior distribution with unbounded variance, like with infinite variance. And also we'll assign to each vj the combination weights for the last layer, the same prior with mean zero and the variance as omega squared over m. So it's divided by the number of neurons in the hidden layer. That's our setting. And then we can prove that we increase the layer width, namely when m goes to infinity, the output of the neural network fx follows the Gaussian process plot. Let's see how can we arrive at this result. So, first, because each transformation weight vector uj has the same prior with some bounded variance. So know that after transformation with x and do some nonlinear activation function, your output neuron will have will follow some distribution, right? Will follow some distribution with bounded variance as well, right? Because uj itself has bounded variance. Then you do dot product with x and do some activation function. The variance should be bounded as well, right? And because every u1, u2 to um, they're independent, then their function, namely each neuron, are independent. So that means each neurons, their outputs are IID with bounded variance. And then we multiply each neuron with the corresponding weight in the next layer and skew them by square root of m, square root of number of neurons. Right? We construct a set of new IID variables. So to this one, right? Because, you know, all those V variables, V1 to Vm are independent, and the neurons like H1, H2 to HMX, they're all independent. So when they multiply together, they're independent as well, right? And second, because each V variable has zero mean, right? And the V are independent to the corresponding H variable, so their mean will be zero as well. Does it make sense? And because also because VG has a variance constant proportional to 1 over m, right? So now if you multiply with a scalar square root of m, then the variance of this guy will be constant to m, because this m and this m is kind of cancelled. Right? For example, like if Vj has a variance, so Vj has variance m over omega squared, right? The square root of Vj, what's the variance? What's that variance? Just omega squared, right? Because you have a scalar here. Right? If you multiply a random variable by some constant, then its variance should be multiplied by the square of that constant to multiply to. So now I multiply with the square root of m in our constructed sequence of random variables. We know that there are ID with zero mean and some constant variance to m. Right? Now, we can represent our output as an average of this set of newly constructed random variables, and then skewed by square root of m. That's the key observation. So why this is true? Okay. We can take a look at our computation of the neural network output. Right? It's just the linear combination of the neurons and with the weight VGs, right? So now inside this summation, I just multiply with some square root m. Okay. And then in the outside, I multiply with square root as well, and then divided by m. So you can see that two square root of m together, it become m, right? And cancel with m in the denominator. That's how we get here. Does it make sense? Okay. So fx, namely the neural network output, actually can be viewed as a skewed average of the ID random variables. Right? So those are random variables and their ID. So why do we arrange the form of x in this way? Because we can apply the central limit theory. So what the central limit theory tells us, right? So it tells us that, like, suppose you got a bunch of ID variables, okay, and the variance of these variables are bounded, meaning that it's not infinity, and zero mean. Okay. Then the central limit theory tells us that the average of those variables skewed by square root of number of variables will asymptotically converge to a Gaussian distribution. That's the central limit theory. It's a very well-known result, right? So now we can see we can just apply the central limit theory here. Right? It just tell us that, okay, your f of x, when m goes to infinity, meaning that your number of averaged ID random variables goes to infinity, the square root of the number of variables multiplied with the average will converge to a Gaussian distribution. This is just a straightforward application of central limit theory. So we can further extend this to any finite number of inputs. Right? So here, I mean, application of central limit theory here, we just talk about 1x, right? So now if we consider you have a collection of the inputs x1, x2 to xn, right? And then your neurons at all n inputs are vectors, right? It is a output of the neuron now will become like sigma u transpose x1, sigma ug transpose xn, right? It becomes a vector, n-dimensional vector. But again, your final output fx now becomes a vector as well. Sorry, it's fx1 to fxn. Right? And you can still represent them as a linear combination of the hidden neurons, right? But here, both the output and the neurons are vectors, meaning that they're evaluated at n inputs, right? But all the construction and observations still hold here, right? Because we can still construct an intermediate random variables square root m and hj and v kj as a set of ID random vectors with zero mean and bounded variance, right? And then you can still represent f in this way. So that means you can still apply the central limit theory. That means your output vector, when m goes to infinity, meaning that you have an infinite number of neurons, the output vector will follow a Gaussian distribution as well. But now it's multivariate Gaussian distribution. What does it mean? It means that for arbitrary finite set of inputs, your neural network output at those inputs, when m goes to infinity, will always follow a Gaussian distribution. So that means your neural output is a Gaussian process. Right? Remember our definition of Gaussian process is that, okay, it's a function, and then your function value at arbitrary input set follow multivariate Gaussian, then it's a Gaussian process. Any question? Yeah, if you're interested, just like think about it. It's a very easy to show that. It's just a simple application of the central limit theory. But yeah, David. Oh, this one? Yeah, that's a good question because they want to construct this one. They want to construct first, they want to make sure that your construction of these guys are independent but with bounded variance. Right? If you don't assume Vj has variance like this, then you multiply a skew with Vj and Hj. You know, when m goes to infinity, it won't have bounded variance. The variance will go to infinity as well. Omega? Oh, which omega? Oh yeah, okay, yeah. Omega, yeah, omega is free. Is any omega square is any positive constant if you like. It doesn't matter. You mean omega square? The omega square really doesn't matter. Because the precondition to apply the central limit theory is that you're gonna have a set of ID random variables with bounded variance. You cannot assume, okay, when n goes to infinity, their variance goes to infinity. Then it won't give you the result. So as long as your omega square is kind of bounded constant, it doesn't matter, right? It doesn't matter. It doesn't matter if it's 1, 2, or 3, whatever. It's bounded. The key is that it's bounded. But when you construct this guy, right? When you multiply square root m with something, right? You know, if you assume V1 has constant variance, is not skewed with m, well, your variance won't be bounded. That's why you have to assume some kind of like shrinker, smaller variance about those weights, like VGs, like when you increase the number of neurons. Okay, that's a very good question. That means you're really interested in the proof. Okay, any other question? Okay, I mean, this is a really straightforward application of central limit theory, but it reveals some profound connection between the Gaussian process and neural network. So that's why, in my point of view, like I didn't see like any essential difference between these two types of models. And this work was recently extended to deep neural networks. So people have shown that even for multi-layer neural networks, not only for one hidden layer, for multiple neural networks, if your number of neurons goes to infinity each layer, and then it will converge to Gaussian processes as well. And also they can derive what is corresponding kernel function. Okay. Okay, so we use one lecture to give a quick introduction to the Gaussian process regression. To summarize, Gaussian process regression is a very powerful non-parametric model for function estimation. It is flexible in that it doesn't restrict to any specific function form. It doesn't assume any parametric function form. Although ideally you can still view it as linear model, but then the feature mapping is really infinite dimensional. So practically you won't be able to do that, right? And there are two views of Gaussian process priors. And for predictive distribution, it is very convenient. You have a closed form. And finally, we have a profound connection between the Gaussian process and Bayesian neural networks. Okay. Yeah, I think this is a so far we have a finished discussion of all the content in our class. We have one final lecture on next Tuesday, which I will just use about 10 minutes to give a retrospect about what we have discussed, and then I will leave it as a kind of office hour. I'll stay there, and if you want to ask questions, like any question, not necessary to be restricted to this class, feel free to stay. Otherwise, like in the next lecture, I mean, you can join, or you can just like after our brief summary of what we have gone throughout this semester, you can leave as well. Okay, yeah, let's stop here today, and yeah, I will thank for everyone's efforts for this class. I'm always knowing that this class is not easy, right? But when I see everybody comes here constantly, I feel very happy. Okay. Hopefully see you on next Tuesday. Yeah.